So in this video we're going to solve the part C of homework 4. So here we're asked to explain the geometric rationale of Lagrange multipliers and use it in the conjunction with Broden's method to find the minimum of 2D Rosenbrock function constrained to a circle which center was at 1 1 and with radius of 0.5. So before doing that, let's understand what a Lagrange multiplier is. So we'll quickly go to Wikipedia page of Lagrange multipliers. So over here you can see this is the basic idea to convert a constraint problem into a such form that the derivative test of the unconstrained problem can still be applied. Okay, then the relationship between the gradient of the function and gradient of the constraint means, okay, let me explain you like okay, so we're taking a function and we're taking a constraint function and we are setting up the relationship between the gradient of the function and the gradient of the constraint. We're going to find the relation. Okay, and they both are related by a multiplier known as Lagrange multiplier. So let me take you here. So it's the part C. Let me move these things. I'll be talking about this bit later, so let me move them down. Okay, we are fine now. Okay, so this is the part C or part 3, you can say part 3. Okay, so here let's take f of x as our objective function which we want to minimize, but with the constraint of this is the constraint function subject to this constraint. Okay, so in our case this is the Rosenbrock function which you need to minimize, but within this constraint of this function. So as Lagrange multiplier, according to the definition, the gradient of the objective function is equal to some Lagrange multiplier, some constant multiplied by the gradient of the constraint function. Okay, and how we are getting this, I'm going to define this. So there is a beautiful picture over here in the Lagrange multiplier Wikipedia page. I've already taken this here, so I'm going to discuss that briefly over here. So let me enlarge this. Okay, so as you can see here, these are the contours of our subjective functions. Okay, f of x equal to d, f of x equal to d2, and okay, f of x equal to d3. So there are different contours, and g of xy is our g of f of xy is our constraint function at some is equal to c. So this also has a constraint line which is passing through all the contours of our subjective function, objective function. Okay, as you can see, there are different gradients at this point, and at this point, only at this point, as you can see, this is the gradient of our objective function, and this is the gradient of our constraint function. So I need to change the color of my pen just to, okay, let me take this blue. Okay, this is the gradient of our objective function, and this is the gradient of our constraint function. As you can see here, these two are collinear, and only at this point we'll be getting the minimum of our objective function subject to this constraint function gxy. If you take other points like this point here, the gradients will not going to be collinear and will not going to get the minimum subject to this point. So the gradient of this point and this point has to be equal, and using that relation we have written this f of gradient of our subjective function, the objective function f of x, which you want to minimize or maximize, is equal to some multiplier, which in case we are taking lambda as our Lagrangian multiplier, multiplied by the gradient of this constant function. Okay, now this could be positive or negative, it could be anything according to our sign convention, but using that we'll define our Lagrangian equation, which is, let me write it here. Let me list this thing out. So L is the Lagrangian equation, x, y and lambda is equal to delta, I can just write f of x y plus lambda into g of x y. Okay, now if you want to take, it will be equating the partial derivative of this Lagrangian equation with respect to x equal to 0 and dou dl dy is equal to 0. And now if you just take partial derivative of this Lagrangian function with respect to lambda, with respect to this Lagrangian multiplier, and equate it is equal to 0, so this will become 0, and from this you can just say that f of xy is equal to minus of g of xy of gradient. We'll take gradient of the function. Okay, it has to be gradient, I forgot. Just need to add them. From this we got this, so just need to add these things to get this equation, and from this we got this relation back again. So this is all about our Lagrangian multipliers. Now coming to Reznik-Brock function. Okay, so in the Wikipedia page you can see, and this is the best algorithm. This is the Reznik-Brock function is used in optimization mathematics, and it can be used as a performance test for optimization algorithms. Okay, so this picture I've already taken here. I just need to show you. So this is the general function which I have taken here, ax minus by square. So the general function over here. So if you let me paste it here and make it large. Okay, make it a bit smaller. Now as you can see here, this is our Reznik-Brock function, and this is used to test the optimization problems. So over here you can see these are the lines, and these are looks like the valleys, and these are the minima points. But in our case, if you take that function which are given at 1 1, these are the minima points. So at 1 1, this point we are supposed to get our minima, but as our constant is a circle with this radius of 0.5, so this is 0.5, and we will just draw the circle like this. So our minima point should come something near this. Okay, so which will be around something between 0.5 to 0.1. Okay, and as you can see, these are very steep points, but if you move along the graph, the values will change very slightly. Okay, as you can see from this graph. So let's do the coding part. Let's go to the coding and see how it converges, and are you getting the values as we discussed in the graph. The values, minimum values should be between 0.5 and 1. So this is our code in Python, where I have defined the Broadens function. Here the Reznik-Brock function over here, and this is the constraint. Okay, now this is our Lagrangian multiplier, Lagrangian function, and let's run the code and we'll see whether it's converging to that point or not. It got successfully optimized, it's not converging, but you need to see where is the minimas are lying. Yeah, exactly as you expected. You got 0.75, 0.56 and minus 0.27. So 0.75, as you have expected, we got the minima at this point, between somewhere between 0.5 to 1. Okay, 0.5 to 1. So yeah, that's it for this video.